everyone, my name is Alberto Marquez. In this video, we will discuss system dynamics. Particularly, we will talk about causal loop diagrams. Causal loop diagrams reflect how one variable affects the other, and we need to make sure that the way that we construct them follows certain guidelines. First, although we may have correlation between variables, what we should be looking for is the causation, not the correlation. What do we mean by that? We mean that we should reflect the structure of the system, how one variable is affecting the other in cause-effect reason, not by virtue of the correlation. Variables could be correlated, but if it is not a physical, chemical, or direct impact of one on the other, then we should not try to depict the world like that. So the main thing is reflect the structure. If there is correlation between the variables, then that correlation should be present in the system as a consequence of the structure, as a consequence of the cause-effect relation between the variables. When we're working with the causal loop diagrams, we should always indicate the polarity of the link. And that is critical because by means of the polarity we define the structure of the system, whether if it's a reinforcing loop or a balancing loop. Besides indicating the sign of the link itself between two variables, we can indicate or should indicate the polarity of the loop. In order to indicate the polarity of the loop, we need to identify if it's a reinforcing or a balancing loop. How do we know that? Well, all we need to do is we need to count the number of negative signs we have in the loop. If we have an even number of negative signs, it will be a reinforcing loop, because every negative sign paired with another negative sign balance as if it was a positive loop. If we had an odd number of negative signs, then it will be a balancing loop, because eventually, while the pairs of of negative signs will be making it a balancing loop, the last and independent, not paired negative sign will make it balance, will make it go against the trend of growing, forcing it to not grow and stay stable, promoting or reducing the amount of change inside that loop. However, in large complex systems and models, not counting would be probably not the best way to go about it. But the best way to go about it is to follow the process, following the loop, and making sure that as we go reading the relations between the variables, we double check if the logic makes sense. It is very easy to indicate in the wrong way a positive sign or a negative sign in any one of these loops, and then that could create problems. So it is preferable to follow the loop. Once we have the loops, we can actually name them, and the variable names should be nouns or phrases, not verbs. And usually what we like to do is to state it in a positive form. So, for instance, if we have happiness, we would like to have, if the variable that it's affecting happiness, we could easily depict that something is reducing the level of happiness. Not so easy it is to understand or so intuitive to say it is increasing the unhappiness. So usually we could use terms that are reflecting a positive sign, and then we decrease that positive sign in our signs. That work better for the human intuition. Another example is if we have profits and we have to reduce profits, then that's easier to understand than an increment on losses. So those two examples should be sufficient to understand that it is better to state the variables and the loops in terms of positive terms as much as possible. We should not build extremely complicated models. The human mind can only grasp so much, and what we could do is do not include everything into a very single large diagram. We much rather have them presented in sections and group all these variables that interact together as part of one section. And then once that it's understood, we can compartmentalize, or once this is understood, we can make them a soup model that has inputs and outputs, and then we don't have to look at it as in the same level of detail, and then we can proceed to explain other parts of the model. Remember, this modeling is not only for purposes of predicting, but a lot of it is with the purpose of communicating with decision makers. So if we have a very complicated model, it'd be very hard to understand the whole system. One of the things that we need to do is identify key variables, and in those variables we should maintain the same level of aggregation. What do we mean by that? If we're talking about the number of flights of an airline and the number of customers and the number of arrivals and the number and the profits that this generates, that's a certain level that is completely different than the dynamics of landing an airplane, and it would not be, you cannot model in a single model all these things together at the level of the profits of an airline and the physics associated with the flight of an airplane. So we should stick to one level of aggregation or the other, depending on the scope of the system that we want to represent and optimize. In the case that we have goals for these variables, we should express the goals in a very explicit way. We must state what is that we want the system to achieve and just state it. That will make it clear for everybody that we're looking for a desired state. The relative magnitudes matter to capture the structure. What do I mean by that? If you have tiny little increments, you will see that maybe you will need to run this simulation for a very long time in order to find the final outcome. If you model gains or the variables and the changes that it promotes are affecting the system in a more dramatic way with a higher magnitude, then you will see that the system is changing. So the combination of the difference in time and the gains and the magnitudes of change in the variables affect the way that we have to run the model and the utility of the model itself. It is difficult to predict, and that's something that we need to take care of. And this is, from that perspective, challenging in selection. Finally, talking about these causal loops, these causal loop diagrams are not perfect. They have limitations. And one is that you can never really finish a causal loop diagram. They're always just provisional as you go learning about what's happening, because we don't know, we always learning about what's happening, and They're never comprehensive. We're always learning what's happening, and we should use it as a tool to learn and grow our knowledge and communicate with other people and to summarize their expressions. But there is no hope of actually finishing a complete causal loop diagram. So in that sense, we can use it as a tool to build our models when we create the flow and stock diagrams, but we should be aware of that limitation. So they are always provisional. We should do not treat them as, or try to achieve perfection. And of course, causal loop diagrams do not distinguish between stocks and flows, and that's a significant difference because having stocks add delays or momentum to the variables, which are not reflected in the causal loop diagrams. So I hope you find this video interesting and useful, and I'll see you in the next video.